So these are the notes for 1.5, where we're dealing with one-dimensional kinematic motion, constant acceleration. So a couple things that we're going to do. First, we're going to assume that, let me get to my drawing, there we go. We're going to assume that T naught is equal to 0. What that means is that the starting time when we start a problem, we're assuming the starting time is 0. What that does is it allows us to say that delta T is the same as T. So in these equations, whenever you see a T, that's really the total time or the change in time that took place. The next thing that we have to assume with this is that acceleration is constant. Now, if acceleration is not constant, we're looking at calculus problems. And we're not really going there with this set of information. A couple things, we're going to rewrite a couple of these formulas. This would be our first kinematic. I really like that version. This second kinematic, or this third one, sorry, I would change this x minus x naught into just delta x. Just like we can set t naught to be 0, we can set x naught to be 0. You might say that the ground below a cliff is 0. You'd say that x equals 0 down here. But we can also come up here and say that x equals 0, and maybe this is now negative 10 meters instead of this being 10 meters. So we have some flexibility. Because of that, I really like to have that be delta x. And same thing with equation number 2 here, the second kinematic. These are our three kinematics. The second one, I actually like to write it as delta x equals v naught t plus 1/2 a t squared. I like that version a little bit better. It's not the only way to write it, clearly. There's other ways to take it, but that's how I like to do that. When you're doing problem solving, especially these kinematic questions, you first need to examine the situation and determine which principles or properties, but we're just throw the word principles. Think about physics principles. Are you talking about acceleration? Are you talking about velocity? Those kinds of things. Maybe you should draw a picture. Pictures really do help us a lot. What we want to do is we want to make a list of what's given, so given information, or what can be inferred. So there's going to be information that's inferred just by the way the problem's written or what's stated in the problem. We want to identify exactly what needs to be found or solved for or gained. So I'm going to say found in the problem. We want to find an equation or a set of equations that's going to help us solve the problem, and then we're going to substitute the knowns along with their units. Now, I'm going to say you don't have to write the units in the equation every time, but you do need to check the units. Are they actually what you say they are? And then, of course, check your answer to see if it is reasonable. Okay. That being said, if we get through that, let's look at some of these problems, example problems, as a way to go through and do that exact thing. I'm going to start here with question number, this little plane starting from rest. It says it accelerates from rest to 40 meters per second in 10 seconds. How far did the plane travel in that time? So we're being asked right away to find delta x. That information must be found. We know that the initial velocity is 0 because it says it's at rest. We know the final velocity would be 40 meters per second. If this was a 40 meters per second squared, that would tell us that it's an acceleration, not just a velocity. And the time we're told is 10 seconds. The issue with this is that if we don't have the initial velocity and the acceleration, we can't solve for something else. In the kinematic equations, all of them require the acceleration and v naught. We have v naught, but we don't have a. So we can't actually find v naught until we know a. Well, if we realize that a is the change in velocity divided by the change in time, the acceleration would be 40 minus 0 over 10. And that comes out to be 4 meters per second squared. Now that we have that information, we should be able to solve for delta x using this second kinematic. Delta x equals v naught, which is 0, times t, which is 10, plus 1/2 of a times t squared. So So that's 0. Half of 4 is 2. 10 squared is 100. So delta x is 200 meters. Okay. To avoid an accident, a car is going to decelerate at a rate of, so this would be an acceleration of negative 0.5 meters per second squared. The reason it's negative is it says that it's decelerating. It says it's going to do that for 3 seconds. It's going to cover a distance or a position change of 15 meters. And the question is, what's the car's initial velocity? Now this doesn't give me the final velocity, but luckily kinematic number 2 doesn't use the final velocity. So I can use the same equation here. Delta x, that's 15, equals v naught times t, which is 3, plus 1/2 of a, which is negative 0.5, times t squared, which is 3 squared. I should simplify down to 15 equals 3 v naught, minus 2.25. If I add 2.25, sorry about that, add 2.25, we get 17.25 equals 3 v naught, and we divide. V naught is going to come out to, I believe it's 5.75 meters per second. Again, when I look at the sig figs on this, it looks like we're looking at 2 sig figs. So really this answer should be written as 5.8 meters per second. Okay, so the sig figs, it's nice to try and make sure that our answers are answered appropriately with the right number of sig figs. If you don't get it right every time, you know, it's going to be something that we talk about more and more as we go. But I'm not, you know, trying to hunt you down over it just yet. So here we have a cheetah that's walking. Okay, here, let's do this. There's our cheetah walking at a velocity of 1 meter per second. It sees a zebra, not a giraffe, just imagine that's a zebra. See there, you can see the stripes. Okay, so it sees a zebra, sorry, it's supposed to have polka dots, right? Okay. Sees a zebra 25 meters away and takes off. The question is, what's the acceleration required so that at the end it's traveling 20 meters per second? Well, we don't have time, that's kind of the catch, but if we look at all the information we do have, this being delta x, we should be able to use the third kinematic, which is the final velocity squared equals the initial velocity squared plus 2 times a times delta x, which is 25. The way we're going to do this is subtract 1, because 1 squared is 1. 20 squared is 400, so that's 399 equals, 50. Let's go back and change that to 50a. We divide by 50, divide by 50. A will come back as, I need a calculator, that's a big number. 399 divided by 50 is 7.98. 7.98 meters per second squared. And there we go. I do believe that that's it. I guess there's one more. The left ventricle of the heart accelerates blood from rest to 26 centimeters per second. If the displacement of blood during the acceleration is 2 centimeters, meaning that's how far it's moved, okay, determine the acceleration in centimeters per second squared. Normally we want this to be in meters per second, but since everything is in centimeters, we might as well do centimeters per second. And then it asks how much time it takes. So first, let's start with the initial velocity of the blood. It's going from rest to a final velocity of 26, that's positive. The displacement, or change in position, turns out to be 2 centimeters per second. First thing we're going to look for is the acceleration. And once we know the acceleration, we should be able to find the time. So to find the acceleration, we're going to have to use kinematic number 3, which says that the final velocity, 26 squared, equals the initial velocity, 0 squared, plus 2 times a times the movement, which would be 2. So this is 26 squared divided by 4 to solve that. So 26 squared divided by 4. I should get an acceleration of 169. That seems big, but it is what it is. 169 centimeters per second squared. If you think about that in terms of if you cut a major artery, blood spurts out pretty aggressively, and that's a big deal. And then the last thing is to find the time. So, how quickly does it accelerate this blood? So if we look at kinematic number 1, it says that V equals V naught plus AT. V is 26 equals 0 plus 169t. So we divide by 169 because the 0 doesn't matter. So we're going to take our 26 divided by 169, and we're going to get 0.154 seconds. Well, because this is in 2 sig figs, it'll be 1.15 seconds. And our acceleration should really be, for 2 sig figs, 170 centimeters per second squared. All right, that's it. Hopefully that helps you enough, and good luck. We'll see you.